Before we move on, I wanted to make two more remarks about this definition of the derivative. So notice, and I'm going back to the box here, notice that the definition of the derivative in this box gives us f prime of x. So this yields our derivative as a function of x. So when we use this limit or this definition of the derivative, we're going to get our derivative as a function of x. So what this allows us to do is, if I know what f is and I get my derivative f prime of x, I could plug in any value, any x equals a, any value to evaluate the derivative at that point. The other thing I want to note is that commonly this notation gets really cumbersome, and it's easy to get bogged down in having x's and delta x's and could look really confusing. So another way that we're going to see this written is, instead of using a delta x, we're going to use an h instead. So we might often see this as the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. So again, delta x and h essentially mean the same thing here, but when we use h instead of delta x, it's just easier to look at. So we can see that definition written both ways, and AP might use those interchangeably. So you will see those written both ways in class as well. So there's another definition of the derivative that we need to know called the alternate definition. And and your spiral, that should be the real number symbol right there. So in the alternate definition of the derivative, this is going to allow us to find the derivative for a particular x value, a specific x value. So for one input. So I'm going to draw on this graph again. It's going to look kind of similar to how we started this. Let's say that we have a point on our graph. And again, I'm going to say that this is when x is equal to a. So our location is a, and our function value is f of a. And I'm going to draw another point on the graph. So when I say a is a value. A is a constant. But let's pick another point. And I'm actually just going to go ahead and call this point, its location, x. So in this case, x is a variable. We could plug in any value for x. We could choose any point for our second point. And again, we have the ordered pair a comma f of a, x comma f of x. And if we were to find the slope of the line between them, well, again, this is not a tangent line. This is a secant line. So when we're finding the slope, we would start with f of x minus f of a over x minus a. That just looks like our slope formula. But if we are wanting to find the slope of the tangent line at the particular value where x equals a, we need to make this into a tangent line. So that means we need to take our point at x and move it so that it's on top of our point at a. So that means we need to take our location on the x-axis and move it so that x approaches a. Oops. So that means, again, we need a limit. We need to take our slope equation and limit it so that x is approaching a. So in this alternate definition of the derivative, this allows us to find f prime of a. So notice this is not a function of x. This is not our derivative as a function. This is our derivative evaluated at one specific value, one input. And we'll also see this other notation that looks like dy dx and then a bar, and then under the bar it says x equals a. And when we see this notation, we're going to read this as dy dx evaluated at x equals a. So again, we have another definition with our limit. This one is maybe a little easier to look at because it just looks like our slope formula. It looks like how we would find the slope between 2 points, but when we limit that so that x approaches a, we're finding the slope of our tangent line, not the slope of our secant line. So in these next couple of examples, we are asked to identify the function and value for each derivative. When we first look at these limits, these might first look like limit problems that we saw in our first unit. And I might notice that in the first example, if I go ahead and plug in a 2 for x, I'm going to get 8 minus 8 over 2 minus 2, which is 0 over 0. That means that I have a hole. So anytime that I'm evaluating the limit and it's really the definition of a derivative, I'm going to have a removable discontinuity like this. So if we are just asked to identify the function and the value, what we need to start to recognize is that structurally, this looks like our alternate definition of the derivative. If it were our first definition, we would either see a delta x or an h in our limit, and that might give it away more easily. So if I think about this, this looks like the limit as x approaches a of f of x minus f of a over x minus a. So if I think about what is my function and what is my value, well, my function, f of x, is x cubed. And my value, a, it's easier to see here or down here, my a is the number 2. And if I think about it, f of 2, so 2 cubed is 8. So I can use f of 2 to check my numerator and see that this is in fact f of x minus f of a over x minus a. So what we are finding when we evaluate this limit is we're finding the derivative of x cubed evaluated at x equals 2. And to clarify something real fast, when we say dy dx, we said dy dx is a derivative. You could think of it almost like a noun. It's a thing. It's the derivative of y with respect to x. We could also write this as d dx. It looks like it's times y, but that's the derivative with respect to x of y. But either way, that is a thing. That's like a mathematical noun. When we see d dx, this is an operation. This means to take the derivative with respect to x of something. So you could almost think of this as a mathematical verb. So just like multiplication is an operation, d dx is an operation. It's the act of taking the derivative. So this notation down here, this means take the derivative of x cubed and evaluate that at x equals 2. That's really what that limit represents. In this middle example, again, if we're in unit 1 and we're just asked to evaluate this limit, we might plug e in for t and get the natural log of e minus 1 over e minus e. Since the natural log of e is 1, it's not 0, the natural log of e is 1, we get 0 over 0 when we evaluate this limit. But here's the thing. None of our tools that we learned in Unit 1 would be helpful here. There's nothing to factor. I can't multiply by a conjugate. I don't have a special property for this. So we would not be able to evaluate this limit if we don't recognize it as being the definition of the derivative. So again, this is written in this same kind of format, the same structure as what we see above. So the limit as t approaches a, so it's just a t, not an x, of f of t minus f of a over t minus a. So again, we could see our function, the function we're trying to identify is the natural log of t. And the particular value a, where we're evaluating our derivative, is at e. So we are finding the derivative with respect to t this time, since that's our other variable, of the natural log of t, and we're evaluating that at x equals e. At t equals e. Sorry, It's getting bogged down by x's. All right, this final example in this section, we might not right away think of the definition of the derivative because we're expecting to see two terms in our numerator. We're expecting to see f of x minus f of a. But if I think about it, it still works out because the sign of pi is 0. So I could think of my numerator as being like the sign of x minus 0 over x minus pi. All right, so when we are trying to determine, again, our function and the specific value for which we are evaluating our derivative, I want to think of this again as our limit as x approaches a of f of x minus f of a, that's our 0. If that helps, we could write a minus 0 there, over x minus a. So again, our function f of x is the sine of x. Our particular value at which we're evaluating the derivative, a, that is equal to pi. So we are finding the derivative with respect to x of the function, the sine of x, and we're evaluating that for when x is equal to pi. So all of these derivatives, again, they would yield a value. This is going to yield f prime of a. So again, if f of x is the sine of x, this derivative is going to find f prime at this particular value, pi. Like that's what this is equal to, f prime at pi. So as we start to work with this definition of the derivative, we're going to see that it can be really challenging. It can be really cumbersome. And our goal is to find some rules or some shortcuts that we can use because we don't want to have to evaluate a limit every time we're using the definition of the derivative. In fact, kind of the opposite. When we see a limit and we can recognize that it's the definition of the derivative, we're going to have some other tools for which we can evaluate that limit. But for the sake of doing one example the long way, let's look at this example where f of x is equal to x cubed, and we're going to find f prime of x. And we're just going to do this once. So again, we're being asked to find f prime of x, not f prime of a. So that means that I have to use my first definition of the derivative that was on page 11. And I'm going to use h just to make our example a little bit easier to look at. So I know that I'm finding the limit as x approaches h, so I'm using h instead of delta x, of f of x plus h minus f of x over h. And again, that's the limit as h goes to 0. Sorry, check that you didn't write the first thing I wrote there. I'm sorry. I was thinking about our alternate definition when I wrote that. Okay, so instead of the limit as delta x goes to 0, this is the limit as h goes to 0 of f of x plus h minus f of x over h. And out to the side, because we're going to actually need to plug in our function value, I might just want to think about this. If f of x is x cubed, then that means f of x plus h is x plus h cubed. So when we go to rewrite our limit, we're going to substitute x plus h cubed for our f of x plus h minus x cubed, all of this over h. And if we plug in 0 for h, for example, we're going to get x cubed minus x cubed over 0, which is 0 over 0. So again, whenever we're evaluating the limit and it's a definition of a derivative, we're going to have a removable discontinuity, aka a hole. So to deal with this algebraically, right now, there's nothing I could factor out the way this is written. So the only thing I could actually do is expand this. We could expand x plus h cubed. Now, you can absolutely expand this on your own, because what we're doing is we're multiplying to get x plus h cubed. We need to multiply x plus h times x plus h times x plus h. And we're going to have to do several distributions to do that. For time, you can trust me, or you could work it out on the side. I'm going to tell you this ends up being x cubed plus 3x squared h plus 3xh squared plus h cubed. And if anyone's learned the trick to do this using Pascal's triangle, that's what I did just now. And if you don't know what I'm talking about, let me know and I'll show you sometime, or I'll add a little something to Schoology about how we can use Pascal's triangle to expand something like x plus h to a power. It's really cool, actually. Okay, so we are evaluating the limit as h approaches 0 of, we said, x cubed plus 3x squared h plus 3xh squared plus h cubed, that's just the first part, minus x cubed. So all of this was just the first part that we expanded. And again, that's all over h. Well, we still have, like, if we plug in h equals 0 right now, we're still going to get 0 over 0. We have yet to remove the discontinuity. But what we can notice is that these two x cubes, I have an x cubed and a negative x cubed. We could cancel those out. And now all the terms in my numerator have a factor of h. So what if we factor out h like it's our GCF, our greatest common factor? So we now have the limit as h approaches 0. I'm going to factor out my h. So I have 3x squared plus 3xh, because I'm only factoring out one factor of h, plus h squared. And this is still all over h. But now, because we could factor out our GCF of h, we could cancel, so to speak, our h's from our numerator. And now when we reevaluate our limit and we substitute 0 for h, well, I have 3x squared, no h is there, 3xh plus h squared. What we're left with is just 3x squared. All right, so what we found is that if f of x is x cubed, f prime of x is 3x squared. Now, that was so much work, and that was a really simple derivative as far as derivatives go. So there has to be an easier way. There has to be a rule or a shortcut, and that's what we're going to talk about in the next part of this video, because we do not want to have to evaluate a limit like that every time we need to take a derivative, because we are going to need to take a derivative starting today until every day for the rest of our calculus lives. So stay tuned. In the next video, we're going to go over how to do that using the power rule.